Let's start again. So a block of mass 1.5 kilograms slides down from rest down a ramp of length 2 meters. Guys, we're just saying that this one can be answered either by using conservation of energy, so from third year, or by F equals ma. The initial height is 0.75 meters above the bottom of the ramp, and the final speed of the block at the bottom was 1.3 meters per second. Calculate the average force of friction acting on the block. So for this one, what we want to do is we want to find the potential energy at the start, at the top, kinetic energy at the bottom. There'll be a difference because there's friction. So that difference in energy will be the work done by friction. And then you use work done to find equals force times distance to find the force of friction. So this is stuff that more of a slightly more complicated part of the third year physics, but it is third year physics. Okay, so first of all, AP at the top is mgh. So mass times gravitational field strength times by the height. Remember, the height is the vertical height, so it's times by 0.75, which comes to 11.025 joules. Okay, I wouldn't round it just yet because you're going to be then using it further on in the question. Kinetic energy at the bottom. Half mv squared. So half times 1.5, and the speed at the bottom of the ramp is 1.3, so 1.3 squared. Don't forget your squared. And that comes to 1.268 joules. So we've got obviously more energy at the top than we have at the bottom, quite a lot more energy. So the energy lost is the difference between them, which comes to 9.76 joules. That's not the answer to the question though, because we're asked to calculate the average force of friction acting on the block. So we want to say the energy lost is equal to the work done due to friction. So work done is force. You can say force times distance, or you probably see in the equation list it is labelled force times S for displacement. So the work done, 9.76, is the force of friction times by the distance travelled by the block, so that's the length of the ramp, so 2.0. So the force of friction comes to 4.9 newtons. If it's all within one question, just round at the end. If it was like part A, find the potential energy at the top, then you'd round potential energy, but because it's all in one, you just round at the end. So that's relatively straightforward stuff that you've seen before a number of times. The second method is using a block going down a slope, so you have to find the component of weight parallel to the slope, so like what we were doing yesterday. So I'll leave that for a little bit because I think some people are still writing. But you'll see method 2, I think, is slightly more complicated, so it takes a little bit longer time, and obviously choose the easiest and the way that you're going to guarantee to get marks. Okay. Can I move on? So method 2, using Newton's second law. So I'm going to redraw the diagram. So this way, you've got to work out a few more things. So that's the force of friction that we want to find. Let's call it Fr. So to use Newton's second law, we also need to know the component of weight that's on the same plane as the friction, so parallel to the slope. That's 0.75. We don't know the angle of the slope yet. However, We do know that that is 0.75 and that's 2 meters. So we can work out what that angle is, call it alpha, by using sine alpha is opposite over hypotenuse, so 0.75 over 2. So the alpha would be inverse sine of 0.75 over 2, which I believe comes to 22 degrees. So already one thing that we'd already need to find out to answer this question, which probably took us just about the same amount of time as answering the full question the other way. Right, so we need to draw the special triangle. So we've got our component, our weight downwards, and our component of weight, and that would be 22 degrees, and that would be 68 degrees. So I'll just redraw that at the side. So we need to find the component of weight down the slope. So the weight is mass times gravitational field strength. The mass was 1.5, so 1.5 times 9.8, which is 14.7 newtons. So cos of 68 would be the adjacent over hypotenuse, so WS over W. So WS would be W cos 68. So 14.7 cos 68. And if you work that out, it comes to 5.5 newtons. We're still not finished. So this is taking quite a lot longer than the other one. 5.5, yeah. Then we can use Newton's second law. So we now know that that is 5.5 newtons, and we've got a frictional force back the way. However, we also don't have the acceleration. We want to find the force of friction, so we'd have to use F equals ma, but we don't know the acceleration, so we're going to have to find that as well. So find acceleration. How would we do that? Super equation. So another step. So it's moving 2 meters down the slope from rest. Final speed is 1.3. Acceleration is what we want to find out. So we'd have to use v squared equals u squared plus 2as. I hope you have enough room on your page. So I think I'm running out of space. So 1.3 squared equals 0 squared plus 2 times the acceleration times by 2. So the acceleration comes to 0.42 meters per second squared. Then we can use F equals ma. So it would be 5.5, take away the frictional force, is the mass times by the acceleration that we just found out. So the frictional force comes to 4.9 newtons. So we got the same answer in the end, but there was quite a few more steps to go through and ways that you could potentially lose marks if you get the acceleration wrong, if you get the component of weight wrong. So there are a few steps that you could slip up on. About probably a 5 marker. Because even with the energy changes, you have to find the energy before, energy at the end, the difference in energy, and then use work done to find the frictional force. So probably 4 or 5 marks. So you see, it's a lot less work doing the other way than this way. As usual, I'll leave that up for a little bit if you want to have a read through the next example. Anyone still writing? Am I okay to move on? Speak it out. Okay. Sorry, are you still writing? Are you okay? You get to move on? Okay. Right. So, example 19. A car of mass 800 kilograms travels up a hill at a constant speed of 10 meters per second. The friction on the car is 100 newtons throughout the climb. First of all, calculate the amount of energy supplied by the car's engine to get the car to the top of the hill. So, that engine is going to have to supply energy for it to go up the hill. So it's going to have to supply the potential energy required for it to climb up the hill, but it's also going to have to supply energy to overcome the frictional force. Okay, so the total energy supplied is going to be the potential energy to take it up the hill plus the work done against friction. So mgh plus force times distance times s. So it's 800 times 9.8. Remember, it's the vertical height, so 25, plus the force of friction, which is 100, times by the distance travelled, which is 500. And that comes to 246,000 joules. Part B says find the power of the car's engine. So power is energy over time. We've got the energy, we don't have the time. We do, so what we do know is it's travelling at a constant speed of 10 meters per second. And we also know that it has travelled 500 meters. So the time is going to be the distance divided by the speed, yeah. So you'll see there's a few sort of like tricksy parts to these questions where it's not always obvious how to do it. So, but you will be able to do it. There is enough information in the question. It's just you've got to go through a few more steps. So 500 divided by 10, so 50 seconds. So the power is the energy divided by the time, which should come to 4,900 watts. Yeah, I just rounded it. Yeah, 4,920 is fine. Okay, have a read through the next question, the last question in the booklet. Are you okay, Rona? Oh. There you go. Right, the last question should look familiar because it is sort of the diagram from one of the earlier questions that we had gone through. So, am I okay to move on? Good. So we've got a man pulls a garden roller of mass 100 kilograms with a force of 200 newtons acting 30 degrees to the horizontal. So remember, we had this guy pulling it before, and we had to work out what the horizontal component was. There's a frictional force of 100 newtons between the roller and the ground. But this time, we want to calculate the work done by the pulling force if the roller moves through a horizontal distance of 5 meters, and then the work done by the frictional force when the roller moves through that distance. So first thing to do is we're looking at horizontal distances, so we need to find the horizontal component of the force. So we've got our 200, we want to find this one, Fx, and it's 30 degrees. So cos 30 is adjacent over hypotenuse, so Fx over 200. So the x, the horizontal component, is going to be 200 cos 30. Remember the cheap way that I did tell you about, if you want to use it, you don't have to, is that 200 has gone through the 30 to get to Fx, so 200 cos is through. You can completely ignore that though if you want to. So part A, so the horizontal pulling force, we want to know the work done by the pulling force if the roller moves through a horizontal distance of 5 meters. To find the work done by the pulling force, so I'll just put an arrow there because it means it's pulling it in that direction. It's force times distance. But we have to use the horizontal component of the force. So 200 cos 30 times by the distance of 5 meters. The reason I don't work it out beforehand is just because it's just easier to write down rather than something point something. So you put that into your calculator, you come out with 866 joules. Oh, have I done something wrong? What did you get? You got 300. Are you in the right mode of calculator? No, yeah, not in this case, yeah. Okay. B, this is where you're probably, yeah, you went too far ahead. So B, the work done by friction when the roller moves through this distance. So we're looking at the friction separately. So I'm going to put an arrow back the way. It's the force of friction times by the distance moved. So that will be, the friction was 100, wasn't it? So 100 times 5. So 500 joules. And C, hence calculate the speed of the roller when it's been moved through this distance. So basically what we want to know is what is the kinetic energy gained. Okay, so he's pulling it forward and he's giving it energy of 866. However, there's also it's having to expend energy of 500 joules. So the outcome energy, the energy that then goes towards kinetic energy, is going to be the pulling energy take away the energy against friction. Okay, so the kinetic energy gained is the work done by the pulling force take away the work done against friction. So 866, take away 500, and that's where you got your 366 from, isn't it? Joules. Okay, but that's not, it answers the question. It asks you to calculate the speed of the roller when it's been moved through this distance. So kinetic energy is half mv squared. So the kinetic energy gains, 366, is half times by the mass of the roller, which is 100, times by the speed squared. So you end up with the speed squared being 7.32 and the speed comes to 2.7 meters per second. Okay, so a lot of sort of repetition of National 5 stuff there, but just expanding a little bit on it.